Hi, in this video, we present our paper, Deep Template-Based Object Instance Detection. Object detection is a key computer vision task for which much of the focus has been on the problem of identifying the bounding boxes of a particular object class in an image. Yet, in contexts such as robotics and augmented reality, it is often necessary to find a specific object instance, such as a red cup in this case, instead of all the objects from that class. A problem for most learning-based detection methods is that they are limited to the set of objects they have been trained on. Testing on a new object is thus not possible, so a new dataset has to be built and a new network must be trained. In this work, we propose a novel end-to-end 2D generic instance detection method. Instead of training our approach for every possible objects and embed this knowledge directly inside the network, our approach generates a joint embedding space from a second input, which contains multiple viewpoints of the target object. This allows our method to successfully detect object instances that were not seen during training. Here we compare our proposed architecture with traditional networks. In common network architectures, a backbone network extracts generic features in the early layers and task-specific features towards the end. During training, this network learns specific features to detect and discriminate the objects it is trained on. Since our network doesn't know the target object in advance, it requires generic and adaptable features. First, we use local templates that extract viewpoint-related information. Inspired from recent object tracking approaches, these embeddings are correlated with the features extracted by the backbone network. During training, since we know the pose of the object in the scene, we only use a single local template, which is rendered with a slight pose perturbation. At test time, we use a stack of templates rendered from 16 different viewpoints in order to retrieve the object in all possible poses. A key component of our approach is to inject information about the target object at the beginning of the backbone network to guide the low-level feature extraction. The features of a global template are correlated in a residual block with the output of the first layer of the backbone. In our experiments, we found that the performance drops by around 20% when this branch is removed from our architecture. For both training and testing, only a single random viewpoint of the target object is selected. Since we use a single global template, the backbone can be computed once at test time. The task network is then computed for each local template after the correlation. Online processing time can be saved by precomputing the global and local features. For training, we use a synthetic dataset rendered with a physics-based engine. We use a total of 125 3D models where randomness is applied to their texture, material, and background to reduce the domain gap with real images. We show here results on line mode and occluded line mode datasets. The methods are divided into two groups, those who are trained with test objects at the top and those who don't need the object in the training phase at the bottom. Our method outperforms all object generic methods on the challenging occluded line mode dataset and is on par with the learning methods trained specifically on these objects. We show some qualitative results on occluded line mode using our network. Green are good detections, blue are false positives, and red are missed detection. In this paper, we have proposed a method for detecting specific object instances in an image that does not require knowledge of the object at training time. Our experiments show that while the network has not been trained with any of the test objects, it is significantly more robust to occlusion than previous template-based methods. It is also highly competitive with non-generic approaches. Our approach, however, suffers from different limitations. For instance, false positives arise from clutter with similar color or shape. Moreover, since the last part of the network is processed for each local templates, the detection is relatively slow.